Hello, we are Group 3, and this is the critical design review for our project Audiovisible. My name is Gustavo Monaco, and I will be guiding you through the next couple slides. The motivation behind this project is to bring music to people who are deaf or hard of hearing. Given that art is an inherent part of the human condition, music should be enjoyed by everyone alike. So this is our attempt to do that. The objective then it is to serve an underserved audience and serve it well by delivering the visual experience of music. Some of the features of this project, the core features will be a multicolor display and audio output. Advanced features will be now a visualization, right? A simulation of the sound waves and or a graphic equalization. We have other ideas as well. However, this is what we think we can accomplish. Now let's talk about the device. Here you can see two different renderings of the device, so what we hope it's going to end up looking like. But at least from a concept perspective, this is more likely what it looks like. So we have identified several different sub-assemblies. In these sub-assemblies, so I guess the first one that we need to acknowledge will be the housing or the enclosure of the device. Then inside of the device, we hope to have a couple of circuits, of printed circuit boards. For those, we're going to have the optical controller and the optical engine. They might be one and the same. We currently are unsure exactly how that's going to play out, but we have at least an idea. Then we're going to have the microcontroller assembly here, which is basically a system on chip, and the computer that's going to be doing the computation and the heavy lifting about that is going to be translating the sound into a visualization. And of course, that needs to be powered, and we're going to have some audio output going on as well. Now we're going to move to the enclosure. For the enclosure, we have some schematics or some initial drawings that we have, only for at least for us to have an idea of where everything should be located. After some moving around, we came up with this like final design. The screen, as you can see, it's also displayed over here. We spent some time picking the screen more than anything else because we needed to have some rear projection onto it, and we decided to have basically a professional level gray rear film that works pretty well. Everything else we plan to construct with recycled materials or just easily available materials, nothing too fancy. In order to ensure that the quality of the image and the technology that we were pursuing was worthwhile, we purchased an evaluation module from Texas Instruments, and the results were actually quite pleasing. The LED brilliance, it's really good under regular room lighting conditions. The distance from the screen to the device is a little greater than we expected. However, there's nothing that we cannot fix with a couple lenses. And there's almost no heat whatsoever radiating from this device. And the image is flipped on the screen because we are projecting from the back. All right, now let's move on to the next component, which will be the computer. For the computing aspect of this project, we chose the Raspberry Pi 4 Model B. After comparing with several other options, we decided on this Raspberry Pi because of the versatility, the power, the availability that it has. It comes with Bluetooth already integrated, and we can easily just capture and connect the phone to it. Now, when it comes into the processing, we can code everything in Python and run it on Ubuntu or another version of Linux that can be installed on a little SD card, and everything can be run from here. The video output, we're going to be using the GPIO pins for that. given that that's the example that we have here in the evaluation module, and it seems to work pretty good. A couple of challenges that we have with the evaluation module running this proof of concept was that it was built for Beagle Black, and the complexities of the configuration on the Raspberry Pi to use the GPIO pins. It requires to have an overlay and to understand the transfer rate and the clock frequencies and a couple of things. More testing is required.
Hi, my name is Marcos Berrios. I'm a photonics science and engineering student here at Creel. I have experience in diffraction-based optical metrology tools, and my current focus is in diffractive waveplate technology. I have a background in music theory and performance, and that's what brought us to this project in the first place. Now that you've learned about the computer, let's talk more about the optical engine. At a bird's eye view, our optical engine is based off of DLP projection technology. DLP projectors create an image by illuminating a digital micromirror device with an RGB diode array. That image is then projected through a lens system and either onto or through a viewing screen. In our case, it'll be through the viewing screen. So because we're making a projector, production of an image is critical to our success. Not only that, the colors that we're producing should be bright and easily identifiable, and they should be bright enough such that they shine through a screen and are able to be viewed by the unassisted eye. So what was our plan? We decided to purchase a pocket-sized projector kit from Texas Instruments, which was fairly affordable, and replace the illumination optics inside with a new optical system of our own design, improving the brightness of the system and making the color mixing possibilities much wider. This is a ZMAX rendering of the original pocket projector optical engine. You notice here at the top is the illumination assembly. Our plan with this illumination assembly, as you see here, it's just LEDs, red, green, and blue, which are collimated and then homogenized to illuminate the prism system. Our plan is to replace the LEDs with laser diodes to increase brightness, and then replace the collimating lenses with ultra-thin diffractive waveplate lenses that I fabricate myself at work using liquid crystal technology. But before I set out to design the lenses, we need to select appropriate laser diodes to meet our needs. Here are all the specifications of the laser diodes we chose. You may notice that they have particularly high output powers, close to between 80 and 100 milliwatts, which we chose and intended in case we need to cut the power with apertures or filters of any kind. The most important thing worth noting here, though, from an optical design perspective, is the divergence of each laser. You'll notice that each divergence angle from each laser is completely different. So we need to design lenses, or I need to design lenses that will collimate them respectively. As you can see, this module is actually quite small. The optical assembly is less than 2 inches across and about 1 inch long. The aperture size of this projector is only about 5 millimeters. That's the kicker. What that means that we need to collimate our diverging beams to a diameter no smaller than 5 millimeters. Due to each laser output having its own divergence behavior, in an ideal situation, each laser would have a lens carefully designed to have a focal length appropriate to collimate all the light coming out. After some considerations and quick calculations, I planned on making the red lens 20 millimeters, the green lens 28 millimeters, and the blue lens of a focal length of 14 millimeters. Now, this is all good in theory, but as I discussed the logistics at work, I eventually realized that due to constraints on time as well as materials, it actually wasn't feasible to design and fabricate 3 separate lenses in the time allotted. The process to design and fabricate these lenses is actually quite intensive, and it takes a couple of weeks, so it might end up not working. To make up for this, I decided to standardize the focal length of the lenses and use apertures to cut out any straight light. Each beam will be collimated by a lens of 28 millimeters to accommodate the smallest diverging lens, which is the green laser. If I made them any shorter, then the beams might not actually be as large as I need them to be. I'd rather have beams that are much larger than too small and don't make enough illumination. So what's next? Due to shipping delays related to COVID and other extraneous circumstances, we've only just received our diodes right in time for the CDR this week. This weekend, I'll be testing the outputs of the diodes. Next week, I will begin lens fabrication at work, which I expect to take 2 to 3 weeks. And then by the second week in October, I expect to have finished assembling the optical engine and be ready to test the module itself.
My name is Jaaquan Thorpe. I'm a CPE. I'll be focusing on the hardware part of the design. So let's go ahead and get started with the optical controller. Here we have a display of our 3 chips. The digital display, which is our display controller, DLP-C2607. Alongside of it is our power management chip, DLP-A1000. And on the bottom right, we have our DMD, our digital micro mirror device. Starting with our display controller, we see that it's a very low power digital controller for display applications, mainly for small display applications like a phone, watches, even very small devices like ours. It supports a pixel clock up to 33.5 megahertz and supports up to 60 hertz frame rates. This device definitely meets our engineering specifications to allow our design to work efficiently. We're working alongside our DMD for reliable operation. It's very necessary they work along together, or our display function will not be consistent. This device will be programmed over I2C, and it also has an external SPI serial flash memory device to ensure that it works correctly. This device comes with a single pin. When it's set to high, the projector powers up and projects the image. When it's set to low, the projector powers down to save some power. Next, we have our power management and our LED driver. Here we see we have some integrated MOSFET circuits. These circuits are definitely important to regulate our voltage, to make sure that each diode is getting the right amount of voltage, and also the current also at the right times. As you see, it says we have a thermal temperature and a light sensor. Those sensors are definitely monitored by our 10-bit multiplexer that's built into our power management, which is the DLPA1000. Very important, essential piece. Without this chip, our device would not be powered correctly. This is a very essential part. Now we have our DMD, where all the magic happens. This digitally controlled micro opto electromechanical system spatial light modulator. In short words, it's saying it's electrical input with a digital output system. This proper optical system pretty much displays image or videos, which is amazing. It's suited for small items, small equipment, as I said before, phones or watches. It has an array of highly reflective aluminum micro mirrors, up to 8 million mirrors. So even though it's a very small device, it has a lot of mirrors. These are the examples of the 3 chips. That's how they looked, top and the bottom where the pins are showing. And to have a better understanding of their sizes, we have a penny here to compare with them. Moving along to our audio output, we attached an 8-ohm 1-watt speaker to connect to the Raspberry Pi to detect the accuracy and show the intention of essential features. This is actually a very important speaker. It will be showing us that our displays are correct based on the analog and output that's being given. So we'll listen to the sounds and the different changes of music and different frequencies. We should see also a detection of change also in the display to ensure that the device is working correctly. With the power input, we include an adjustable AC/DC power adapter, which we only need 5 volts to power optical module. So this beautiful universal adapter has many different ports, so we're probably using the smallest port to save space on our PCB. This adapter has 5 to 15 volts adjustable options, and we'll be choosing the 5 volts. Of course, this will be used mainly for the prototyping portion of the project. In the top left, we have 6 NMOS switches. These switches here are for the turning on and off of the different laser diodes. We need those. We need that. It's very important for not every light to be turned on at the same time. Some lights will be turning on at very high speeds, changing, just to ensure the display is clear and also accurate. In the bottom, you have the DMD regulators for the digital micro device. These different 5 modes of operation are essential to regulate our DMD to ensure that it's being turned on at the right time, turned off. Also, it gives power at the right times and removes power, so that's very important. 5 modes of operation. We begin the off mode when our device is disconnected and has no power. Once we connect to the power, we transition to standby mode. In standby mode, we can either connect to the power or be defaulted to standby mode when we reach our thermal shutdown threshold when the temperature gets too high on the device. Once the controller signals the DMD to display something, we move into active 1. The DMD supplies are powered up. Even though we are powered up for the DMD, the strobe decoder is still disabled. That is when it's time to actually display, the strobe decoder is enabled in active 2, which allows the different micro mirrors and different LEDs to be turned on and off.
Hi, so my name is Danielle Garsten. I'm a computer engineering major, and I'm part of the Department of Electrical and Computer Engineering. My main focus is on artificial intelligence and mixed reality. I hope to pursue a career in software engineering, and I aspire to pursue a higher level degree such as a master's or a PhD. So here is our software design and approach. As you can see on the right over here, we have our waveform code from a microphone. So this is what we're going to be using to test it out, is be able to retrieve sound from a microphone where we can be able to see the waveform. So here is our software approach. Our first approach is to be able to get the Python code to be able to detect a Bluetooth signal from a phone and be able to retrieve that Bluetooth signal, so send and receive. And then once we know that's working, we want to be able to create a simple neural network with that signal and be able to get components of the sound such as beat, pitch, harmony, and take those elements and be able to put them in a node and have them each classify as something such as the size of the visual, the color, the shape, etc. Then we want to make a simple visual on a computer. So our original goal is to be able to create a waveform or something simple such as like a circle or a triangle, and then that way we know that it's working and eventually make it more complex. And once we know that that simple visual is working, we want to put it on the Raspberry Pi. And once we know that the Raspberry Pi is properly working, it's sending it correctly throughout the hardware and projecting that simple waveform, we just want to double check it, make sure all the hardware is good, all the software is properly set up alongside the music, and then once it passes all the test cases, we want to increase the complexity of the visual. So here is our software design. Our software design is essentially going to be in Python, where it's going to be able to receive the Bluetooth code, be able to get the song, eventually send it throughout the hardware, and be able to play out the music at the same time as projecting the visuals. It will then detach components, as I said earlier, from the music and be able to put each of those components in a node and be able to coordinate each of those components to a shape or a color. And then our embedded piece will be able to allow the software to run throughout the hardware and for it to process it throughout the optical modules. And our hardware piece, or our Python piece, is going to be able to just essentially get our visuals. We have a really simple user experience and user interface. It's essentially just going to be an on and off button, and everything is essentially in Apple Music or Spotify, which is the fast forward, rewind, skip a song, go back to another song, pause, stop, change the volume and such. Everything is essentially on a device or a smartphone. So once that smartphone is connected, it's really simple to be able to just use your phone to control everything, and it makes it a much more satisfying user experience. So here we have the sonochromatic scale. Over here you can see that each color is coordinated with a note in music. Since both of those hold a frequency, it essentially matches the frequency of that note to the frequency of that color. So essentially that there's different octaves, and in each octave there's different notes with different pitches, and we essentially want to take those different notes and different octaves and be able to coordinate them with a group of colors or a certain color or a very specified color. And here we have the budget and finance. We have all of our supplies. We actually spent way below what we were predicted to spend. We spent about $211, and the budget we have available is $289. So we were initially thinking we were going to spend about $500, but we actually spent about $211, so less than a little over 50% of our money is saved. So we're very efficient when it comes to saving money. So with our completed tasks, we have gathered all the parts, we planned out the hardware, and as for the software, we left a guide on how our plan is going to be able to tackle the software, but it still needs to be completed, and the optical assembly is essentially 95% completed. Here's what needs to be completed is the software. Basically, most of the software needs to be completed. Our hardware is, for the most part, complete. We're still optimizing in EagleCAD and eventually going to send it out to PCB vendors. And then for the optics, we just need to attach the optics to the hardware and make sure that it works. So here's our successes and difficulties. Our difficulties were definitely lack of time, coordinating meetings, and just making the same mistakes over and over again. We feel that it was definitely, we took on a huge challenge that in this about 7 months that we had, especially during COVID, we feel that if we had a bit more time, it would definitely be a much more optimized, much more attractive device. But as for successes, we were able to get ahead and plan ahead. Our communication has been stable, and no one really has delays in communication, and we're able to immediately give a response to one another. And we respect one another, we are very honest with one another, and we have meetings twice a week that are scheduled, so that way we don't get off track of what our project and make sure that everything is complete. So here's our plans for success. We just want to be able to get the PCB, attach the components, finish the setup of all the hardware, complete the software, and run that simple waveform test, and then eventually make a much more graphics intense visual, but that is down the road. Our main goal is to essentially get that waveform and make sure it plays alongside the sound. Thank you so much for listening to our presentation.